chemist wants to find the empirical formula and a molecular formula of a compound that contains only carbon, hydrogen, and nitrogen. The complete combustion of 35.0 milligrams of the compound produced 41.1 milligrams of H2O. A 65.2 milligram sample of the compound was analyzed for nitrogen, giving 35.6 milliliters of N2 gas at 740 torr and 25 degrees Celsius. The diffusion rate of the compound as a gas was measured and found to be 38.2 milliliters per minute. The diffusion rate of argon gas under identical conditions is 58.0 milliliters per minute. Find the empirical formula and a molecular formula of the compound. Okay, so the first thing I'm going to do, since I was given milliliters of N2 that was produced from the 65.2 milligram sample, is I'm going to solve for N. I already converted the torr, the 740 torr, converted to 0.974 ATM. I converted my milliliters to liters. And now I am ready to solve for N. And N is going to equal 1.42 times 10 to the minus 3 moles of N2. Okay, so what I did was I solved for moles of N2, but I need moles of N since nitrogen is diatomic. So I took the moles of N2 and I converted it into moles of N. I'm going to use the moles of N later on. Okay, so what I did here was I took the moles of N of the single nitrogen atom by itself, and I converted that into milligrams since the sample it came from was weighed in milligrams, so it's 39.8 milligrams of nitrogen into the 65.2 milligram sample of the compound. So what I'll do next is, since I have the information for the bigger sample, I'm going to go ahead and use that sample, and I'm going to set up an equation to solve for milligrams of H2O, since I know that the 35 milligram sample of the compound produced 41.1 milligrams, and then I know that the second sample is 65.2 milligrams, and that's the one I want to use. Okay, so what I did was I set up an equation to solve for X being the milligrams of H2O made from the 65.2 milligram sample. This was the 35.0 milligram sample made 41.1 milligrams of H2O. So I put the smaller sample over the larger sample, and X being the sample I want, the milligrams of H2O I want to know. So when I solve for X, I get 76.6 milligrams of H2O. So now I know two things about my 65.2 milligram sample. I know the milligrams of nitrogen, and I know the milligrams of H2O. Now I use the milligrams of H2O to find the moles of hydrogen. Then I'll know 2 of the moles and how much they weigh, which I could later subtract from our sample size. Okay, so what I did here was I took my milligrams of H2O and I converted that into moles of H using the molar ratio here. I then took my moles of H, which I'm gonna save this because I'm gonna need that later. I used my moles of H to find the milligrams of H. So now I know the milligrams of H and the milligrams of N, and that will help me find the milligrams of carbon that's left in the compound. Okay, so I have my sample size. The sample size I chose to use was 65.2 milligrams. I'm going to subtract the 39.8 milligrams, that's nitrogen, and I'm also going to subtract the 8.58 milligrams of hydrogen. This gives me 16.8 milligrams of carbon, And now I'll use the milligrams of carbon to find the moles of carbon. Okay, so I used my 16.8 milligrams of carbon, and I converted that into 1.40 times 10 to the negative 3 moles of carbon. I will now find the empirical formula. Okay, so to find the empirical formula, we're going to take the element with the least amount of moles, which is in this case is carbon, with 0.00140 moles, and we're going to divide each number of moles by the smallest, which is carbon. So moles of carbon divided by moles of carbon is going to be 1, and moles of hydrogen divided by moles of carbon is going to be 6, and moles of nitrogen divided by moles of carbon is going to be 2, giving us an empirical formula of CH6 and 2. So we've solved half of the problem. So now we're going to use the rates of effusion that we were given in the problem to find the molar mass of the compound, the molecular molar mass. And then we'll divide that by the empirical molar mass. So our empirical molar mass will be 46.08 grams per mole. So that's the weight of the empirical formula. Now we'll find the mass of the molecular formula using the effusion. Okay, so what we have here is the rate of argon, which was given to us, which is 58.0 milliliters per minute. I put that over the rate of the compound, which was 38.2 milliliters per minute. Set this equal to the square root of the molar mass of our compound, which we don't know, over the molar mass of argon, which is 39.948 grams per mole. And what I'm going to do is I'm going to square both sides to get rid of the radical symbol. So I squared this side to get rid of the radical. Over here, I'm going to go ahead and divide these and square them and get 2.31. There are no units because the units cancel. Now I'm going to multiply both sides by the molar mass of argon, which will give me my molecular mass of my unknown compound, which will be 92.1 grams per mole. So here I have my molecular weight right here, the molar mass of my molecular formula, and I'm going to divide that by the molar mass of my empirical formula. This is going to equal 2. Now I'm going to take my empirical formula of C6 or H6N2, and I'm going to multiply that by 2, and this is going to give me my molecular formula, which is going to be C2H12N4, and that is what we are looking for.